method. So last time I told you about applications of density functional theory, and it was a question, what is density functional theory? And I told that it's a method of solving Schrödinger equation with replacing it with system of equations. So we replace Schrödinger equation with system of equations. We solve this system of equations, and we tell this that these results are somehow connected with the results we can get from Schrödinger equation, but we can't solve the original Schrödinger equation. And today I will tell you a few words about Schrödinger equation. I think you know all of this information, but I will repeat it. It's always a good idea to repeat some scientific information. And then I will tell you about Hartree-Fock method. So Hartree-Fock methods is the first attempt to solve, to replace Schrödinger equation with some other equation, to solve these equations with iterations. So this method is works as iteration scheme, and then say that the results of solving these equations, system of equations, Hartree-Fock, we will find the solution for Schrödinger equation. And we'll start from the very beginning. Schrödinger equation is like Newton laws for mechanics. It's very hard. It's the core of quantum mechanics. And yeah, right. Okay, so it's the core of quantum mechanics. It's the most important equation in this science, and we can get all information about material, about electrons, about atoms, just solving Schrödinger equation. But the problem is that we can't just take and solve Schrödinger equation. So it was obtained. It was get by Erwin Schrödinger in 1925, and it was published in 1926. And I thought obtained because he didn't derive it. He didn't derive the Schrödinger equation, so he knew some. By the time it was known that electrons as well as light can show duality nature, so they can behave as particle and they can behave as wave. And Schrödinger just took wave equation, which was known from 19th century, and replaced it with quantum things, with de Broglie wave and other things. And he got this. He got his equation, and he didn't want to publish it first time because he thought that it's not the good way for physicists to take some new equation in such a way. Just take an old equation and improving it by new knowledge. But then he published it, and it was a great achievement, and he got a Nobel Prize in 1933 for this equation. So we have two kinds of Schrödinger equation. We have time-dependent Schrödinger equation, where psi function, wave function, depends on time, and we have time-independent or stationary Schrödinger equation, which we don't have any dependence of time. Psi is a wave function, so it's some function which contain all information about our quantum system, and it depends on coordinates r and vector r, and from time, or it don't depend on time if we look for stationary equation. Hamiltonian is some operator which contains all physics of this system, and h is just Planck constant. So it's very this information. Oh, and yesterday I found this picture It's a grave of Erwin Schrödinger and his wife Anne-Marie. And here we see Schrödinger equation on his grave. It's time-dependent Schrödinger equation. I thought maybe it should be time-independent as they're dead, but somebody decided to use time-dependent Schrödinger equation on the gravestone. Okay, what about Hamiltonian? Hamiltonian contains all physics of the system. In the very easy one-dimensional problem, it contains just kinetic energy of some particle, for example, electrons, and some potential, some external potential. We can consider some systems as the electron moving in some potential field of atoms, and we just need to create Hamiltonian for such system, and then substitute this Hamiltonian in time-independent Schrödinger equation and solve it, and we will get all what we need. And T is kinetic energy, so its operator of kinetic energy is minus h squared divided by 2m, and the second derivative. It's the most simple case. And now I will show you some examples which I think you knew from bachelor courses. For example, connections with harmonic oscillator. We have this problem is from its school problem. We have spring with some mass, and it oscillates. So it oscillates with frequency omega, and its amplitude is x. So its biggest amplitude is x. And according to Hooke's law, on this mass, on this ball, will be applied the force minus kx. So it's just Hooke's law from school, and we can create the equation of these oscillations of such mass, or if we have some pendulum, pendulum, yeah. Yes, and you have the same equations for the spring and for pendulum. So x second derivative x plus omega squared x equals 0. So this is equation of oscillations, and our Schrödinger equation can be written in a very similar form, in very similar way. So So here we see wave function, second derivative of wave function. Then we see just normal wave function, and here we can see just normal x, and here is some multiplier. To m h squared minus q. So it can be compared with this omega squared, and we can say that okay, it's a differential equation, second order differential equation in form of oscillations. And then we can solve this equation, Schrödinger equation, as we can solve this oscillation equation. And few examples how we can do it. For free particle is the most simple way. We are taking our Schrödinger equation, time independent. Then we use U external potential equals 0 because it's free particle. So free particle moves in some kind of vacuum. There are no fields. Then we discarded U, And now we have this equation. Second time derivative of psi plus 2m h squared e psi. And then we can solve it the same way we can solve this equation. So how we can do it? We just take x in the form of cosinus or sinus. So for example, we can take a cosinus something, omega t minus something we call delta, substitute here, and we will have this and this constants, omega and a. Зрозуміло? The same way we can solve this equation. We take k squared equals this thing as omega squared, and then we can take the E energy, and we see that energy of free particle is not quantum. So motion of free particle is not quantum. It's just непрервний. Just continuous. Just continuous movement. No, I think it's not the best word, continuous, but okay.
It's actually okay. It's either discrete or continuous.
Discrete or continuous? Yes. So a motion of free particle is continuous. Another example, infinite potential well. It's also very simple example. We just take U, our external potential, in this way. We say that in most cases it equals infinite, and from 0 to L it equals 0. So we have two zones. We have one zone below 0 and more than L, and we have this potential equals infinite. And then we get potential equals 0. And we solve two border conditions. First border condition, when x equals 0. We will solve this equation in this form. So we take some psi function, wave function, which depends on x, in this form. Some constant c1 sinus omega x plus some another constant c2 cosinus omega x. We don't know this constants, but we should get them. We will take x equals 0. Then we'll get that c2 equals 0. We can just substitute 0 here. We see that sinus 0 equals 0. Cosinus from 0 equals 1. So c2 equals 0. Then we just will substitute L. So c from L here we get 0 because we know that c2 equals 0. We get sinus omega L equals 0. So sinus omega L equals 0. It's very simple trigonometric equation. Sinus omega L equals 0. That's why omega L equals NP. N is some number like 1, 2, 3, and so on. And we can get energy from this case. So we get omega NP on L, and then we get energy. And we see that energy of particle in infinite potential well quantizes. So it's quantum because we have a lot of infinite number of separated energetic levels. So energy level 1 when n equals 1, energy level 2 when n equals 2, and so on. We have a lot of levels which goes as some stairway. Then we can calculate psi function for this case. So it's also very simple. We just substitute our omega in our psi function equation. Use some things as that psi function model psi function squared integral over all this space equals 1, and then we can get C1 square root from 2 on L, and we can get this this equation for psi function. So energy levels will be in form of some stairway. From 1 is the ground state level, 1, 2, 3, 4, 5, and so on. 1 is the lowest energy level of this of the system, so it's called ground state. And then we will calculate ground state energy of our systems, of our crystals, or molecules, or some surfaces. And what about psi function? Psi function for different n, we can see here. So for n equals 1, we see just this simple function from 0 to L. Then for, when we take n equals 2, we have 1 node. So the number of nodes will be equal n minus 1. And so if we will increase n, we will increase the number of nodes, and this wave function will be more complicated. But if we will take this psi function squared, we'll see that. So what means psi function squared? Psi function squared means some probability of yes, the probability density. So we can it's probability of finding some electron in some space. So for example, for psi1, we see that the most probable location of electron is the center of this space. So from 0 to L, and the highest probability will be somewhere in the center. For second wave function, you see that the highest probability will be here. So it will be L4 and L34. Yeah, here and here. For psi function with n equals 3, we see that we have 3 peaks. So so our probability density will be more complicated. And in the same way, we will work with crystals, but in crystals, psi function will be much more complicated, and we will work with 3D dimension, with not 1D dimension as I choose for this case, but with 3D dimension. But the idea will be the same. We should get psi function, then squared it, and then we will get some energy, some probability of locating the electron. And the last case which I want to show you is hydrogen atom. Hydrogen atom is much more complicated than infinite potential well or than free particle. For hydrogen atom, we should use Coulomb potential minus K E squared by R. Then we substitute this potential in our equation, but it's much harder to solve it. I will not do it, and because it will take. I think it's a topic of the whole lecture, maybe 2 lectures for some quantum mechanical courses. Solving of Schrödinger equation for hydrogen atom. It's the simplest system. We have only one proton with plus, and we have only one electron with minus. We have Coulomb forces between them, Coulomb potential in this very simple form. So here is a plot of this Coulomb potential, but it's hard to solve it. So I'll just show you the result. Here is the result. Here is energy levels for hydrogen atom, and you see how it locates. We see this Coulomb potential. Here is, so it goes from infinite, from minus infinite to R approximately. So it don't cross the R, this potential. And then we see here is E1, energy 1, energy 2. So it's energy 1 is ground state energy. When we will calculate all our systems, we will looking for this energy, E1. Calculating energy 2, energy 3, energy level 4 is much more complicated than calculating ground state energy. And in most cases, we don't need another energies. So in most cases, we can get all information we need. For example, we need some band structure, we need some density of states, we need some maybe optical properties we can get from this ground state energy. So energy of hydrogen atom quantizes it quantizes in rather hard way, and it's psi function for hydrogen atom. So it I think I hope that you had seen this function before. It was on your courses. So we can divide it into 2 parts. One part is radial part. It depends of some radius from some distance from center of coordinates. And another part is angular part. So here's angular part. And from this angular part, we can get a lot of beautiful flowers, a lot of orbitals. Here I wrote 3 quantum numbers, N, L, M. N is principal quantum number, so it's the same N as we got from solution for infinite quantum well, potential well. It's the first number, second number. Yes, second number is L, orbital or angular quantum number, and M is magnetic quantum number. And for example, here, 2, 0, 0, it's S orbital. Yeah. So it's S orbital, just second principal quantum number, L0, M0, and we get some spherical orbital. For 3, we can obtain the same picture, but for L1, we have p orbitals. So it's p orbital located. We have different orientations for p orbitals for 1 and 2, 1, 2, 1, 1. Then we move to d orbitals. So we go to 3. So here we see 5 d orbitals. dxy, the dxz, something like this, x squared minus y, x squared minus y squared, and so on. So we have for third principal number 3, we have much complicated picture. We have d orbitals, and then we have f orbitals. So that's how we can show you this is how we can illustrate this hydrogen wave function. It's a picture from Wikipedia, and I like it very much. So I think this picture is beautiful, and it's rather simple. So you see these quantum numbers, and you see which combination of quantum numbers gets which orbital, what orbitals get from it. And it's only hydrogen atom. It's really hard to solve only hydrogen atom, but it's much harder to solve some random system, not system with one electron and one proton, but for system with more electrons. So it's Schrödinger equation. It's in the very, very general form. Here we see kinetic energy for all particles. So it's kinetic energy for electrons and for atoms. Here we see some potential which creates this, creates these particles. And here we see all external potential. For example, we have some convex atom, and in this term we will see interaction between electrons and ions and between ions. So so this term can be very, very complex. Then we have psi function, which depends on all coordinates of all elements in our system, and we should get this energy. And how we can get it? We don't know. We can't get this energy from from solving this equation analytically, because nobody knows how to solve it analytically. That's why we should make some tricks. We should use some life hacks to substitute this equation by some another equations which have the same solutions or very close solutions to Schrödinger equation. And first methods to do it is Hartree-Fock method, and it's a topic of another part of my lecture. But before it, I will tell you about very useful approximation. It's Born-Oppenheimer approximation. Okay, first, a few words about these two guys. Max Born is one of fathers of quantum mechanics. So he was one of the first guys. And if you heard about Copenhagen interpretation, about its Born's work, if all these things with wave function is Born's work. So Born have told that psi function squared is some probability density. So it was Max Born's idea about probability density. So he's one of the greatest scientists who ever lived. Robert Oppenheimer. Have you watched the movie about Oppenheimer?
Very funny story. I watched exactly half of it, and then electricity got cut off.
Okay, I hope I will not spoil this movie. Okay, Robert Oppenheimer, we know him as the father of nuclear bomb. So, but it's not he wanted to do in his life. He once told that he was born he was born too late. He was born too late to be one of fathers of quantum mechanics as Max Born, and Max Born was his teacher. So in the movie, in the first part of the movie, not the second, in the first part of the movie, we see Oppenheimer in Germany, in some room. He has some kind of depression, something like this. It was the time when he worked with Max Born. And it was a time when they made this Born-Oppenheimer approximation. Oppenheimer thought that he was born too late to be a father of quantum mechanics, but he became father of nuclear bomb. So I don't see that he was very happy because of this fact, but it's history. Okay, Born-Oppenheimer approximation was so this two tried to simplify Schrödinger equation. They thought, okay, we have very in general form. Okay, let's take Schrödinger equation in very general form, and Hamiltonian in general form. What it will look like? So here we will have kinetic energy for atoms, for ions. Here we will have kinetic energy of electrons. Here we will have some interaction potential energy between electrons. So Ri and Rg, it's distance to one electron and to next electron, and we go for all electrons. Then we have some interactions between ions, and then we have interaction between ions and electrons, and it's too complicated. We can't solve it. And Born and Oppenheimer thought, okay, electron much smaller than ion. That's why we can neglect of ion's motion. So it moves so electron moves so quickly that we can say that ions are almost stable, and we can just remove this thing from equation. And we can remove kinetic energy of ions from equation, and then we can say that, okay, this thing will be some kind of external potential. We have some Coulomb potential of stable ions, and it's not so hard to calculate this potential. It's much easier to calculate than we think that they are moving, and we should calculate this potential in each time. It's just another representation. Tn, Te. Tn is ions energy, Te electron energy, kinetic energy, Wee interaction between electrons, and N interaction between nuclei, between ions, and Ne interaction between nuclei and electrons. And that's the idea of Born and Oppenheimer. It's very simple idea. Just to take this huge wave function for this for equation for this Hamiltonian, and divide it for just nuclei, and then discard it, and divide it for electron part, which depends on electron coordinates, and some potential field from these ions. And then we can solve system of equations. So what I told you, that we don't solve the original Schrödinger equation. We just solve some system of equations. Born and Oppenheimer created from one very, very hard to solve Schrödinger equation to not so hard to solve Schrödinger equations. One Schrödinger equation just for ions, and then they just discarded it. So in most cases, we will use stable ions. In our equations, in our laboratory works, we will use stable ions. And here is Schrödinger equation for just electrons. And it's simpler than original Schrödinger equation. And then we will take this Born-Oppenheimer approximation, and we will so we will take this part, not this part, but this part, and we will simplify it much more. And this simplification made Douglas Hartree. He was a mathematician. He was interested in physics. That's why he made some calculations for quantum physics, because you see, he was born in 1897, and it was time when quantum mechanics has born. So first, so it's the birth of quantum mechanics is 1901, when Max Planck made his speech in Berlin or 1900. I don't remember exactly. So it's the very beginning of 20th century. 20th century began from quantum mechanics. And Hartree made another simplification. So we have our Born-Oppenheimer approximation. So this. So we will work with this equation. We discard this, and we will work only with this. This equation without nuclei, just electrons. And then he told, okay, we can't solve that equation from a Born-Oppenheimer approximation because it's still too hard to make it. It's still too hard to solve it. That's because in that equation we see we have two complex wave functions, because this wave function depends on a lot of coordinates of each electron. And then he thought, okay, just made some simplification and imagine that our complex wave function consists of a lot of independent wave functions. Each wave function for each electron. That was Hartree's idea. That was his approximation. So he just took very complex system and he thought, okay, we will divide it for a lot of much simpler wave functions for each electron. And these wave functions should be orthogonal, so they should be independent. That was the idea of Douglas Hartree, and he made a lot of good things with it. He made this. So we can calculate. We want to get energy of the system, energy of system which describes by this set of wave functions. We can calculate it in this way. So it's bracket gives Hamiltonian in the bracket of these psi functions. Then we can represent this complex wave function in the number of just independent wave functions here, and it's just Hamiltonian. It's just kinetic energy and potential energy. So nothing special. Then he took this as one part of equation, this as another part of equation, and he made you see here you see only for I, and here you see for E and G. So, and this thing is the most complex thing in Hartree-Fock method. He told this. Douglas Hartree told. So we have some how to say it? We have a complex wave function. We divided it for a lot of independent small wave functions. And then we have Hamiltonian, which consists of original Hamiltonian and some part which was created by this. And then he got this thing. So it's Hamiltonian. And this is some kind of exchange interactions between one electron and another electron. You see. Psi-E, Psi-G, Psi-E, Psi-G. Here we see only one, only E. And here we see E and G. And this term, he told, he told this thing calls Hartree term. Hartree term stands for interaction between electrons. Here is it. So not in the form of wave functions, but in the form of integrals. It just it looks like Coulomb potential. So n alpha Жите, what is it? It's just it's just psi function squared. Yeah, just psi function this multiplies on psi function this, and we get some kind of electron density. So we have here electron density, and here we have distance between these electrons. So it's kind of Coulomb interaction. It calls Hartree term, and it will we will have this term in density functional theory. It's very important term for it, because here we see some density. We get here some electron density, and another part of equation very common. So it's kinetic energy. So it's some kinetic potential. It's external potential. Hartree energy, which I described now. This one electron wave function and one electron energy. And Hartree, by doing this simple thing, as dividing complex wave function on simple wave functions, he gets set of equations. So he gets a lot of equations. Each equation stands for one electron. Зрозуміло ідею? I hope that you understand it. Okay, and maybe you can see the problem of this thing. Maybe you can say the problem of it. I can say the problem here. The problem in the first approximation. If the problem is that for Hartree method, we use only bosons.
So wave functions should be independent.
The functions are independent, yes, but you see, we don't when we multiply this one electron wave functions, the sign of huge wave function don't change. So when the sign don't change, it means that we works with bosons. So when we take psi functions for bosons and then multiply them, sign of huge wave function will not be changed. So it works only for bosons. And if we want to work with fermions, we should include the case when sign will be changed. For example, we take psi1 and psi2, multiply them, and we get minus psi something. And Vladimir Fock made this thing. So he included fermions. That's why we call it Hartree-Fock method. So Hartree method was only for bosons, and it was first method. Then Vladimir Fock so he improved this Hartree method for fermions, and he included fermions in this way. So he told, okay, we will not have such simple multiplication. We will have our psi function in some kind of determinant. It calls Slater determinant. It's some it's for conservative нормировка. Okay. Norm conservative, yeah. So psi function in Hartree-Fock methods will be divided in a lot of one electron psi functions in the form of determinant. It calls Slater determinant by the name of scientist who invented this, who derived this determinant. And things gets worse. So this method became much more complicated. Okay, few words about Vladimir Fock. Vladimir Fock is a Russian and Soviet scientist. I think he's He's also one of the greatest scientists of 20th century, and he is a man of hard fate because he lived in USSR. So he was twice in jail. In 1930s, he for several years have worked in Kharkiv. He worked in Ukrainian Institute of Physics and Technology. Now it's Kharkiv Polytechnical Institute, which was heavily damaged by Russian forces last year. And Vladimir Fock worked there for several years. But in 1937, the group, it was very powerful group. It was very important for physics, and it was very important for physics educational group. For example, Lev Landau worked in Kharkiv at the time. Lev Shubnikov, scientist who invented a lot of things in superconductive science, Lev Shubnikov. So it was it was institute with a lot of brilliant physicists, a lot of brilliant scientists, and even Niels Bohr in 1934 visited Kharkiv. So it's a photo in Kharkiv, Niels Bohr, Lev Landau, Vladimir Fock, and a lot of other scientists. But in 1937, a lot of these guys were murdered by Soviet regime. A lot of them go to jail, and Vladimir Fock was one of them. So he was in jail some time, but he was luckily, because you see he lived for 74. He was luckily because Piotr Kapitsa and some international scientists as Albert Einstein, they wrote to Stalin that you should free Vladimir Fock, and he was freed. So in this way, he was luckily. So he wasn't murdered by Stalin regime. So it was a few words about his life, and he invented these methods when he worked in Kharkiv. Hartree-Fock method. So how it connects to Ukraine? It connects to Ukraine directly. Okay, we can rewrite energy in some way. We can calculate it. Okay, bracket Hamiltonian, and then we divide this energy into three parts. One part is just Hamiltonians, it's nothing special. And another part, we will have two integrals, G integral and K integral. So it's the thing which I told more difficult than in Hartree method. Because in Hartree method, we got only this Hartree energy, this mystical Hartree energy, and Hamiltonian. And that was all. Hartree energy, which stands for Coulomb interaction between electrons, and some Hamiltonian with external potential and kinetic energy operator. But in Fock method, Hartree-Fock method, we will have some new entities. We will have just common Hamiltonian, which is not too interesting, and then we will have Coulomb integral J E G. So this Coulomb integral, it stands for Hartree energy. So it's just for Coulomb interaction between electrons. But this term can be very so it's not so simple as we think, because we can have in one atom, even in one atom, we can have 10 or 20 or more electrons, and we should include all interactions between these electrons in this term. So this term can be very huge and difficult. And this term even harder, so it's even more difficult. KEG, it stands for exchange integral. Then in few lectures, we'll talk about exchange correlation energy. So exchange correlation energy is some part of density functional theory, and it's the energy we can't calculate. So we have only some approximations, but we don't have the exact equation for this and for this. We have exact equations only in forms of these psi functions, but in forms of something we can calculate, some with integrals and some others, we don't have it. So we don't have this and this equation.
I'm sorry, what's mathematical difference between those two integrals? As I can see, you can just rearrange the terms.
Yeah, it's a difference. You see, the difference is not okay. At first glance, they're almost similar. Yes. Here you see psi e, then psi e complex conjugated. Then you see psi g complex conjugated, and just a normal psi g. But here you see psi e complex conjugated. Here it was normal. But here we see psi conjugated and psi g. So we exchanged it. So we have here we have psi eta and psi e convex conjugated. Here we see psi eta convex conjugated and psi g. That's why it calls exchange integral.
Would the result of the integral mathematically be the same if you just multiplication just
in some very particular yes. So we can make some artificial particular case where these integrals will be the same, but in general case they are not the same.
Operator is the definition of operator. K E J is an operator. That's just an integral.
P and J is just integrals, but here we see, but here we have wave functions. These wave functions, they are very complex functions, and we can't interchange them. We can interchange them, and okay, and you see, okay, all these integrals is part of much more complex picture, because they're here, and we then we sum these integrals e+1, g+1, and so on. So they look like very similar, but they are not similar. And this integral we call exchange because we just took this integral, Coulomb integral, and exchanged the psi functions. We took this psi function, psi zeta, and took it to this part. And we took then psi eta and took it to this part. So we exchanged them. That's why it calls exchange energy. And what is the nature of this exchange energy? Nature of Coulomb integral is rather obvious. It's just electron to electron interaction, Coulomb interaction. But for exchange integral, nature is much more complex. It's quantum nature. We have spins for electrons, and electrons with differently oriented spins will be interacting in different ways than electrons with the same spins. So electrons with the same spins, they will repulse from each other, and electrons with differently oriented spins will they will go to each other. And this term stands for this quantum nature. We have this term only because we have spins. It's spins nature. And why we get this term from Slater determinant? Because it's for fermions. Because for fermions, spins are very important. That's why we didn't have it. We didn't have this exchange integral for Hartree method, but we got it for Hartree-Fock. Okay, and the last slide. how we can calculate Hartree-Fock. So we will next time we will have laboratory work, and we will have we will make self-consistent calculations. How one can calculate energy of some system using Hartree-Fock methods. First step, he should input some coordinates of atomic nucleus. For example, we have some crystal, diamond crystal for carbon atoms. We should input coordinates of atoms in some unit cell. We take unit cell with few atoms, we should input coordinates of these atoms. Then we should make some initial guess for molecular orbitals. We can just take hydrogen molecular orbitals, then combine them. It's a linear combination of atomic orbitals, combine them in a linear way, and then we should solve Fock matrix. Fock matrix. Fock matrix is this thing. So we should solve this thing. We should find energy, Hartree-Fock energy. We will have not so good solution. So we will have not so realistic energy because we had rather bad initial guess. That's why we see if this energy consists of if this energy consists of the external field. If no, so if the difference is too high, we should do it again. So we take a solution of the Fock matrix. So we will take some psi functions from here. We will substitute it here, and we will have this cycle until our psi functions will consist with average psi functions. Okay, in Hartree-Fock method, we think that we have a lot of independent electrons, and one electron it moves in the field which created by all other electrons. Not by one electron and another electron and third electron, but in some mean field of these all electrons. And we will our calculation will be converged when our psi function for one electron will be very close to this mean psi function, because this electron it's not some particular electron is not unique in the system. So its electron psi function should be close to this mean psi function. And then we say, okay, we got the solution, and we can calculate energy, and we can calculate some other properties. And so this is Hartree-Fock method, and it's the very first iterative scheme for Schrödinger equation solution. Next time we will make laboratory work in which we will make some self-consistent calculations in density functional theory, not in Hartree-Fock, but in density functional theory. And then I will make another lecture about upgrade of this method, about density functional theory.